Well, welcome once again to Vaptronics Mountain Labs here in Blackhawk. I, uh, I am hoping to be able to introduce and demonstrate today a Hewlett-Packard 8654A signal generator. This unit is approximately 40 to 45 years of age, and it's in remarkable shape for that. It's clean. Very few scratches or abrasions. A little bit of missing paint chips here and there, but overall, very pleasant. The vinyl is in good shape, clean, good handle. It's a fairly hefty unit, but we can see rubber feet we mounted on the bottom, and on the back we have a auxiliary port or power lead coming in. The 8654A was Hewlett-Packard's first all-transistor signal generator replacement for their tube line that had run through the 60s. I believe it was an HP606, which that's the number that comes to mind. But anyway, the earlier tube type generators used, they were cavity type generators, and when they went to the transistor unit here, they went to an LC oscillator type circuit, and successfully came out with this what was a considerably less expensive, good performer. The generator provides a stable, clean, mechanically adjustable frequency between 10 and 520 megahertz, and it does it in 6 ranges. This range switch will switch 6 times. We go from 10 to 18.6, 18.6 to 35, 35 to 66, 66 to 130, 130 to 250, and then finally 250 to 520 megahertz with the range switch. Each time you switch the range switch, you mechanically change the tuning dial indicator behind. Let's see if we can show you that. You can see the dial has changed. And then you're free to mechanically tune the unit across that range. It has a constant metered adjustable amplitude that it can put out, and 14 different ranges of output amplitude measured in both dBm and in volts on the lower scale. And then we have a vernier that allows us to change that voltage, and we meter it up topside, so you can see me changing the voltage. And right now we are on 0.3 volts, so I'm going to adjust myself to the max here at 3. And we also are capable of producing both AM and FM modulation. And we have a internal 400 hertz or 1 kilohertz selectable modulation signal internally. Or we can choose to throw it to the external side, in which case we feed an external modulation input, AM here, FM here. If we push in this button on the meter dial, it goes from measuring the output signal voltage to demonstrating or displaying the modulation percentage. Now, like right now, if I put myself on internal modulation, push that button, we see that we are now reading almost, reading 100%. If I change my my setting here and go back and punch the button again, we see that we've changed our percentage of modulation. And that only works for the AM modulation, not for the FM. So we're going to take the unit through some tests. We'll first test the frequency output, and we're going to take a look at the signal generated on the scope and on our frequency counter, and then we'll also take a look at our spectrum analyzer. Right now we're on the lowest range. We're reading 10 megahertz. Got the dial adjusted for 10. We're reading approximately 10 megahertz on the frequency counter. We see a displayed 10 megahertz signal on the oscilloscope. And I also have my displayed 10 megahertz peak on my spectrum analyzer, and I've adjusted it for full scale display with a 10 dB per division display. So that's going to mean more to us in a little bit. Right now, let's just go ahead and we're going to rotate the mechanical dial. We see the tuner changing its position. If we watch the scope, we see the trace start to squeeze in and display more signal on the display, and we see the counter rising constantly. We're going to take her up to about 18 megahertz here, because that's easy to see on the dial. Okay, that would be 18 megahertz, right about there. And we see that we've achieved 18 megahertz on the frequency counter. Relatively close. We can bring it up just a little bit better. Looking at that counter. The counter is getting its signal from the auxiliary output on the back of the unit. And so right now we're getting 18 megahertz, and there's our 18 megahertz signal. Let's go ahead and change the range. Now we're going from 18.6 to 35. We happen to be setting closer to 35, so we're gonna go to the 35 position. Right there. You see we have 35 megahertz on the frequency counter, and there's our 35 megahertz signal on the scope. We're going to bring it down to the bottom of the range, and as I do so, you can see the frequency spreading out smoothly, and the counter is going down. I'm going to take it to the 20 range here, because it's just easy to see on the indicator. So that would be 20 right about there. 20 megahertz. There's our 20 megahertz frequency on the scope. Let's go ahead and change our band. 35. Let's go to 35 here. Right about there. So we see 35 on the tuning indicator, 35 on the frequency counter, there's 35 megahertz on the scope. Let's go ahead and take her up. And we see the frequency on the scope increasing. We see the frequency on the counter increasing. We'll go ahead and we'll take ourselves up to 65 megahertz. right about there. 65 on the frequency counter, 65 on the oscilloscope, 65 on the signal generator. Let's go ahead and change the range again. We're on the 66 to 130 range. We're setting up on the 130 mark right now. So there's 130 megahertz on the counter. We're getting beyond the range of my oscilloscope, but I can see it there. Still looks like a nice clean signal. We're going to take a look at our spectrum analyzer now. We're looking for 130 megahertz. We'll change the dial here till we get to 130. There we see the peak coming in there. And 130. Right about there. All right. Let's go ahead and drop it down. We should be able to see the scope spreading and frequency dropping. See the counter dropping. We're down to the lower level on the tuning indicator. It's showing 70 megahertz. We have 70 megahertz on the counter. There's 70 megahertz on the scope. The scope and the counter are parallel. So amplitude on the scope is going to vary because of the effect of the counter. That's part of it. We're going to take care of that when we take a look at the amplitude variation later, a little bit later. Right now we're concentrating on just getting a nice clean signal and observing the frequency output. Okay, let's go ahead and change ourselves from 130 to 250 megahertz on the scale here. We just did that. Go down to the 130 mark, about right there. There's 130 on the counter. There's 130 on the scope. Increase the amplitude a little bit. Still looking clean. We've got it on the spectrum analyzer. It's 130. Let's go ahead and raise ourselves up to 250 megahertz. I can see the dial indicator going up. I can see the frequency on the scope increasing, and same thing on our counter. Let's change our counter input. There we go. As we're going up to 250. A little light would help. Alright, we get to 250 right about here. And we have 250 on the frequency counter. 250 on my scope, which my scope has a bandwidth of 100 megahertz, so we're pushing it, but we can see that we do have a signal there. It's very hard to see. But we'll rely now on the spectrum analyzer to show us the 250 megahertz signal. Here we see it coming down. There's 250 right there. All right, and then finally, let's go 250 to 520. We're at 520 right about here. There's 520 plus on the frequency meter counter. My scope has given up any chance of reading it. Can't do 520, not on this. I have a 350 megahertz top end on my spectrum analyzer. So let's take ourselves down to 350. What about there? There's 350 on the counter. I have a smudge on my scope. Doesn't help us much. But on our spectrum analyzer, we should be able to start to see the frequency, 350 megahertz frequency coming in. Here we go. There's 350 right there. So I've been able to display the output up to about 360 megahertz from 10 to 360, but from 360 to 520 I just don't have the means other than I can indicate on my frequency counter. I can't show you the signal itself, but I can show you that we are counting the signal, and as I continually raise, we'll be able to see that the signal goes to beyond the 520. Alright, there's our 520 right now, and I actually have a little bit more that I can generate. Here's 530 right there, and we are at the end of the dial. So we're getting a signal output all the way up to from 10 to 530 megahertz on this unit. The question might be at this point, how stable is that signal? Well, it's clean, it is stable. But how about the amplitude? Is the amplitude relatively constant? Let's take a look at that. Okay, we've got ourselves on the 250 to 520 range. We have the dial setting at 350 on our frequency counter. We have our output level at 0 dBm or 0.3 volts. So we're calibrated on the 0 to 3 scale. And we see on our spectrum analyzer, we see that we are on the topmost of the gradical across the scale. So we have 1, 2, 3, 4, 5, 6, 7. We have 8 divisions. We are on the top of the 8th division, within 0.2 of it anyway. And we are using the 10 dB per division scale. We have this pushed in. And what we see, if I was to take this dial and change the range, we are now on the 130 to 250 megahertz range. We are setting approximately on about 188 megahertz on the dial. When we see 187, 186.6 on the frequency counter. Our meter is still setting on the 3, and our output level is on the 0 dBm still. You didn't touch it. So we're going to have to adjust our frequency on the spectrum analyzer, get us back down to 186.6, and we see ourselves displaying the there we go. And what we notice is that we are still setting, actually we're right on the very top division of our 8 divisions. And let's go ahead and change our scale again. We are on the 66 to 130 range. We are now sitting at about 92, 94, 90, about 95 megahertz on the scale there. On our frequency counter we see 94.59, about 95. And we see that our meter is still setting on the 3. We're still on the 0 dBm or 0.3 volt output level. And we need to reduce our frequency to 94, 95 actually on the spectrum analyzer. We should see, as we approach that, we see the signal coming in. There's 95, and we see that we are just a hair, maybe 0.1 divisions above the top gradical, 8 divisions up. Okay, we're going to go ahead and change again. We're on the 35 to 66 megahertz range. We're running 45, 6, 7, 8, 48 and a half, 49, somewhere in there. 48.33 on the frequency counter. We still see that we're reading 0.3 on the metered output, and we were going to reduce our frequency on the spectrum analyzer, get us down into the 48 range, and we see the signal coming in right about there. Alright, what do we see? We see that we are about 0.1 divisions above the top line again, just like we were a moment ago. So the change in frequency didn't affect it. Let's go ahead and go to our lowest. No, okay, this is 18.6 to 35. We still have one more range to go. We are now outputting approximately 26 megahertz. We still show 0.3 on the, excuse me, we're setting on 3 on the meter dial and 0.3 volts on the output level. We're showing 25.8, 26 if you round. And if we reduce our frequency on the spectrum analyzer to get us to 26, 25.78, and we see again we are right on the top bar of the 8 divisions. So we really didn't vary at all. Let's go ahead to our lowest level. Our lowest level right now is 10 to 18.6. We're running about 13.8 megacycles. I've got to take my frequency counter input to a lower range. Okay, so we're reading 13.65, 13.7 megahertz. We still are on 3 on the metered output, and the output level has not changed. We need to reduce our spectrum analyzer to get us down into the 13.7. Here we go. And it is perfectly on the line. So we varied approximately 0.1 division from from 13.6 all the way up to 500 megahertz. And that 0.1 division at 10 dB per division, that's somewhere around 1 dB. So we did well. If you were to double that, which I don't think there was any way that I needed to, but 2 dB over that range. That's a very constant amplitude as we change the ranges. So now we ask ourselves, okay, what about the accuracy of the metered output? We saw that it was constant, but is it accurate? Good question. We are right now on 13.65 megahertz, and I can display that easily on my scope. Okay. All right. And we are telling ourselves right now that we have an output of 0.3 volts RMS, according to the meter. 0.3 volts RMS converted to a peak reading would be 0.424. So, okay, we're at essentially 14 megahertz. Let's make it 14. There's 14 megahertz on the dial. We have an output. We're on the 0 dB, 0.3 volt output. We're reading 3 on the scale here. We have 14 megahertz on the counter. We're taking the output and feeding it into our oscilloscope with a 50 ohm terminator on the line there, and then we're displaying the voltage on the scope. So we needed to we had to output into 50 ohms to properly read the voltage coming out. And what we see here, we're on the 0.2 volts per division. We are 2 divisions up, so that's 0.4, and then we go just a little shade beyond it. We're just about to the 0.2. So 0.3 volts out of the Hewlett-Packard unit, that's 0.3 volts RMS divided by 0.7071 would give me 0.42 volts peak, and I should read 0.42 volts peak, which is what I just did. If I was to reduce the output level, I am now on the minus 10 dBm, 0.1 volt output, and that means on the scale, I go to the upper scale and I adjust myself till I read 1 on that scale, which I do. I read it right about there, and then I come up to my scope. I'm going to reduce my sensitivity. I'm increasing my sensitivity. Get me something I can easily read. We're on 50 millivolts per division right now, and I see I have 50, 100. I would have 150, but looks like I'm about 0.2 divisions down from that, so 148 millivolts, so 0.148 maybe. What I see here is that with a 0.1 volt output divided by 0.707, I should get 0.1414, and I definitely have 0.14. Let's reduce it again. We're on minus 20 now. I am on the 30 millivolt output scale. That means I need to move my needle back to the 3, right about there. And with 30 millivolts, I should be able to get 0.042 volts out of my scope, so I should get 42 millivolts out. Let's go to the 20 millivolt per division, and I see I have 2.2 divisions, so that would be 42, yeah. So I got 42 millivolts here. That is what I expected. Let's go ahead and reduce ourselves. We go to the minus 30 dBm position, and that is 10 millivolts output, so I adjust my needle to read on the 10 on the upper line. And up here I'm going to change my scale to something I can decipher. Right, I'm at 5 millivolts per division. So I see 5, 10, 15, just shy of 15 millivolts. And what I see is that for 10 millivolts, I should have seen 14 millivolts out. Well, I was just shy of 15. 14 would hit it. Okay. And let's go ahead and take ourselves down one more level. We're on the minus 40 dBm, 3 millivolt level. Means I have to adjust my meter to hit the 3 on the end of the scale here. There we go. And I have no more sensitivity on my scope, so what I have is what I can read. And what I see is I'm about 0.5 millivolts per division, and I have roughly 0.8 plus divisions, so 0.4 something. And what I should have had is 4.2 millivolts, so yeah, I've got 4 plus 4.2. I can't go any lower, and yet my output level goes lower. So how do I demonstrate anything more here? Well, what I'm going to do is I'm going to take myself back up and adjust my output a little bit here. We're going to come back to my spectrum analyzer. We're going to adjust the spectrum analyzer. Okay. Spectrum analyzer is showing me a full 8 divisions, and I'm right on the top of bar. And we can adjust that for 14. Close enough. And as I change my output level from 0 to a minus 10, I see that I've dropped 1 division. Well, I am on a 10 dB per division range right now, so I just reduced myself 10 dB. And on my output level, I reduced myself 10 dB. I went from 0 to a minus 10. I'm going to go from minus 10 to a minus 20. And I see I am now 2 divisions down. So I've gone down 20 dB. Minus 30. And I am 3 divisions down. Minus 40. I am 1, 2, 3, 4 divisions down. 50. 1, 2, 3, 4, 5 divisions. I'm just a hair above 5 divisions there. 60. 1, 2, 3, 4, 5, 6. a little bit above 6. 70. Just about down into the trough here with the noise. I can limit some of that noise, but if that's going to help me much, let's see. Alright, we see 1, 2, 3, 4, 5, 6, 7. We're 7 divisions down, that's 70 dBm. And that's exactly what we're showing on this unit is we're minus 70 dBm from where we started. Minus 80. And now we are all the way down to the bottom of the spectrum analyzer. So I'm beyond the sensitivity of what I can read. I still have 1, 2, 3, 4 more ranges, so can't display them meaningfully, but have every reason to believe that they are working just fine. The unit is calibrated and output level, working fine. Alright, let's go ahead and take a look at modulation. We are currently at the 14 megahertz range. We are running approximately 0.3 volts output. I have my modulation in the AM position. I'm on 400 hertz internal, and I've got myself counterclockwise on my variable. We're going to take a look at our oscilloscope signal, and I'm going to go ahead and start to turn up the modulation. There we go, we start to see the modulation. That would be about 100% there. And if I come over to my meter and I push in my percent modulation, I see that I'm running just about 100% here. And we can go back. Let's see what we are there. Right now we're displaying about 20% modulation. I just increased it, and we see we're running about 0.2. 1, 2, 3, 4, 5. So each one of those is 2. 2, 4, 6. So it'd be 0.26, 0.28, 0.4. So about 26%. Running about 26% modulation on that. I could increase it again just a little bit. And here we are running about 40% modulation, pretty close. We could turn off our AM modulation. We could go to FM. Take a look at our signal. I go to FM, and I increase my modulation. And what we should see, we see a thickening of the waveform as the frequency modulates. Right there we should have pretty clean looking trace, pretty sharp. And then as I turn it up, we see it start to fuzz out and get thicker. And it does. Let's go ahead and take a listen though to the modulation on an FM receiver. Just to hear it. We could go to 1,000 kilo. Let's go ahead and do the 1,000. Alright, there's unmodulated, and there's modulated. Unmodulated, modulated. Alright, let's go ahead and disconnect ourselves from the scope. Just going to drape this cord near my FM receiver. going to take my FM receiver to a blank space, about 102 megahertz right now. And we will find ourselves coming up. Now you can hear the signal. You can see my signal strength indicator. We're at 102 on the 102 megahertz on the frequency counter, corresponding to 102 on the indicator here. And as I change the internal modulation to 400 hertz, you can hear it. Back to 1,000. And then turn up my modulation, turn down my modulation. There's no doubt that it is modulating in FM. I can hear it just fine. Okay, well, I think I've come up with a kind of an interesting test of the FM modulator on this 8654. And what I'm going to do is I'm going to go ahead and feed a signal from this DVD CD player. I'm running a cord on up into the modulation input on this unit. I've got the output of the unit. I've got this BNC cable just sort of draped over my FM receiver, and I tuned the FM receiver into a spot on the dial that was vacant, so we're running about 90, 95 something on the dial. And I'm going to go ahead and I'm playing some music on the DVD. I'm feeding it into the modulating input. I'm going to go ahead and flip to it. I've got myself tuned so that the generator is tuned to the signal on the FM, and we should be able to hear it because we're going to be turning this into a transmitter. So let's give it a try. All right. So is this for sure it? Well, if I change the frequency, I can bring it back in. And there we are, centered again on the channel. Flip off the modulation, flip on the modulation. I can come over here to the unit and I can stop the music. We can go ahead and play again. Start it somewhere else. And the amazing thing is, it sounds darn good. I don't want to play too much of the songs because I'm not going to be worried about royalty problems here. But at least we were able to test and show that the unit was not only putting out a nice stable frequency that we were able to lock into on our FM, but the modulator produced a very nice high fidelity modulation that we were able to listen to on the stereo. So there you go. Nice little test of the modulator. So there, I think we have it. I pretty much have presented what I can, present my case that this is a nicely working unit in good shape. And along with it, we will provide a manual for the 8654 signal generator. It covers everything from theory of operation to performance tests and service and replaceable parts. We've got some diagrams in the back here. And then we also have the original tear sheet with the specifications for this unit on the front cover. So we'll give you that. I would thank you for listening to me and taking a look at this marvelous generator. I'm going to wish you happy bidding. And until next time, bye.